All right, so welcome to lecture number 9 of the course on programming and data structures. So, in the last lecture this week, we looked at comparing the implementations of linked lists with doubly linked lists. The way we did that is we took a single problem, and in this case, it was big integer addition, and we looked at the advantages of maintaining the number in a linked list over maintaining the number in a doubly linked list over maintaining it in a singly linked list. The way we did that was we ensured that our program not only performed the arithmetic operations but also presented some statistics about how many times pointers were traversed when the data was maintained as a linked list and when the data is maintained as a doubly linked list. This gave us a experimental way of comparing the efficiency of two implementations. One of the things that we did not do in the last lecture was we did not look at uh, how much memory was used, and we will definitely do that in the course of a few lectures. But today what we are going to do is we are going to compare a linked list implementation against an implementation with an array. So essentially, at the end of this week, we would have seen three data types: linked lists, doubly linked lists, and arrays. And we will have a clear understanding of what purpose, what data structure, what data type serves. And again, what we will do is we will look at look at one particular problem, and we will um, write two programs, or we'll essentially write one program with two different functions, right? One solving the problem using the doubly linked list data type, the other solving the problem using the array data type, and we will print out statistics of which will be representative of the efficiency of the two implementations. That will help us come up with a concrete comparison. The problem in question for today's lecture is the well-known binary search algorithm. Recall that, and if you don't know, then it's a very easy problem. It's a very interesting programming exercise. You have sorted data, and you can assume that the data is sorted in ascending order. And the question is that you are given a key and you have to check if the key is present in the sorted data set or not. The approach is very simple. Right? You will kind of check the median element, right? And check if the given query item is the median element or not, or whether it is smaller than the median element or the larger than the median element. Depending upon the comparison result, that is whether it is smaller than the median element or larger than the median element, we shrink the size of the search space. The list size shrinks by a factor of 2, right? So because you're comparing with the median element. This is the idea of binary search, and it is often used as an introduction to efficient search procedures, and you might have heard or studied that kind of log n comparisons where n is the total number of keys which are there are required by binary search. Right? But today what we are going to do is we are going to explore the relevance of the underlying data structure. Remember that I said n sorted keys are available. I did not tell you whether they were present in a linked list or whether they are present in an array. Right? And what we are going to do today is we are going to compare and contrast the two implementations, right, with respect to efficiency. In particular, we will come up with an estimate of which one is more efficient than the other. And that will essentially be the last lecture for this week, and we will also look at the implementation of these two programming exercises in today's lecture and talk about what we will be doing in the next week. Right, so now I'll just go to the slides. Alright, so comparison of binary search, lists versus arrays. That is the focus of today's lecture. Alright, so let us just look at binary search. We've already discussed it. The input to binary search is a search key and a list of data items stored in ascending order. Now, when I mean list here, I do not mean a linked list. We will come to the data structure storing the items in a couple of minutes. Okay? The output of the binary search procedure is a fail value. You can either return -1 or some special symbol saying that the search has failed. If the search key is not in the list, if it is found in the list, our goal is to return a location value. In other words, a pointer to the particular location that contains that value. Let's also assume that the data items are all distinct data items. There are no repetitions. Okay. So which is better? Right? So do we store the elements in an array or do we store the elements in a doubly linked list? Right? So observe that a doubly linked list is better than storing in a linked list with respect to time, because the number of pointer accesses, as we have seen, are reduced when we move from a singly linked list to a doubly linked list. Right? We of course use more space when we implement a doubly linked list. Right? So how to quantify the space we've not yet done, but as a qualitative statement, one can always say that one uses a little bit more space essentially to store one more pointer per node. Okay, so today's lecture, as I said earlier, is a comparison between these two. Right? Do we store the elements in an array or do we store the elements in a doubly linked list? So let us just become familiar with the binary search procedure, and more importantly, the focus of this slide is to show you the arguments to the binary search function. The first one is the list itself. Right? The second one is the starting index in the list, which is important, right? And the final index of the list and the value of the search key. Let us understand the arguments. The question here is, in the list, starting with the index start and ending with the index end, is the search key present between these two indices? This is the goal of the binary search function, right? To answer yes or no and return a pointer to the position where the key is present. Right? I hope this is clear. So now what we do is we take the middle element. Let's say this is the median. Right? Let's call it the median in the sorted list between the indices start and end. Now we compare the median element with the search key. If it is equal to the search key, then you have found it. On the other hand, if the median is larger, then we recursively search to the left of the median. Right? What do I mean by the left of the median? We search in the region start index to the predecessor position of the median for search key. Otherwise, we search to the right of the median. That is, we look at the successor of median up to the end of the search region for the search key. Now, of course, it is very important for us to say when we will report that a search has failed to find the key. Right? If start and end become the same, then if search key is not in that particular location, then we report failure. Okay? The other way of thinking of it is that when the start and end cross each other and you have still not found the search key, then it means that the search key is not available in the given data set. It's a small exercise to formally write a mathematical argument which supports this. Right? So if binary search reaches a situation where the start and the end values have become equal or they have crossed, meaning that start index has become more than end index and the key is not yet found, then you can safely assert that the key is not there in the given list, given sorted list. So this is the algorithm. It's a fairly straightforward and very nicely specified recursive algorithm. And we are going to today analyze whether storing it in the list or storing it in a doubly linked list or storing it inside an array is better. Now to understand the exercise, understand and design the appropriate data structures, let us understand where the computational effort is. Okay, the computational effort is in finding the location of the median. Right? Now that's the most important thing because you need to take the middle element. Right? And therefore we need to find the location of the median. That is, you take the sorted list and pick the median. Now, the second thing is that you need to compare the search key with the median value. But observe the total number of comparisons is only log of the size of the log of the total number of elements in your list. That is, it is the logarithm base 2 of the total number of elements in the list. The reason is what is here in this blue color callout. In every step, the search range shrinks by a factor of 2. In other words, if you started off with say 32 elements, after the first comparison with the median element, the search range will shrink to the value 16. Then it will shrink to 8, then to 4, then to 2, then to 1. As you can see, 2 power 5 is 32 and we have performed only 5 comparisons. Log 32 is equal to 5. Now, we believe that this cannot be significantly improved. That is, the number of comparisons that you perform by binary search cannot become smaller than log n, right? Where there are n elements in the list. However, we will see how efficient we can make this problem of finding the median element in the list, right, in the sorted list. So the goal is the following, right? So we started off with binary search and we've now localized and come to the most important question. We want to find the location of the median. Okay? So how does one find the location of the median? Now let us consider two cases, okay, where let's consider the case, let us assume that we know the size of the list and then consider two cases. Okay? Now if the size of the list is known and if we store the sorted keys in an array, right, of that particular size and they are sorted in ascending order, then the median is right in the middle location of the array and a single arithmetic operation, which is the start index plus the end index divided by 2 gives the location of the median. It is a small exercise that each of you should complete on a sheet of paper. Check that if you want to find the middle element, it is the start index plus end index divided by 2. Now if the elements are arranged in a linked list, let us assume that they are arranged in a doubly linked list. First we need to find the total number of elements in the list, right, which is the size. Then we have to traverse size by 2 pointers to get a pointer to the position containing the median element. I hope this is clear. So if you have like 32 elements in the list, right, and the median element is the 16th element, so you must traverse 16 pointers starting from the start pointer to get to the list, get to the position containing the median element. Therefore, each pointer access is considered as one single operation, and one can assume that this single operation is same as in time to a single arithmetic operation. In other words, you can think of this as a single CPU instruction, right? One arithmetic operation compared with one pointer access operation. So clearly, to get to the middle element of the array, only one arithmetic operation is required, no matter how large the array is. On the other hand, if you store the data in a list in ascending order, then to get to the median element, you have to use the size of the array divided by 2 pointer traversals to get to the median element. So therefore, using an array is better when compared to the list for binary search. Right? Now this is a qualitative statement. What we will do in our program is to write the code in a very careful fashion and run it, and we will see the output, and it will give us a proof that our qualitative interpretation is indeed justified. Of course, one can do a mathematical proof, which is what is done in a formal data structures course, right? And I encourage you to look at the material in the formal data structures course. But today what we will do is we'll write a program and we will come up with a experimental estimate that storing the data in an array is better for binary search. So this is the programming exercise for which we are going to take a look at the code. We want to compare binary search when implemented using data stored in an array, sorted data stored in an array, and when the sorted data is in a doubly linked list. The output, let me just make the small correction. Yeah. Right. So when the sorted data is stored in a doubly linked list. Right. So what we will do is we will print out the following. We will print out the answer using both the methods. In other words, we will print out whether the given search key is being found or not. We will also print out the total number of pointer accesses in the case of the linked list implementation, and we will print out the number of median position calculations in the case of an array. And we will see how much effort is involved in both of them. Alright, so now let's go to the program. So I hope the focus of the exercise today is clear to you. We have two data types, the array data type and the doubly linked list data type. We want to come up with a comparison of the two of them. So we choose a programming exercise, the well-studied binary search algorithm, to search for a key in a sorted list. And we are going to implement binary search using the two data structures. In one implementation, we will use the doubly linked list, and the second one we will use the array. And we will print out statistics of how many arithmetic operations were made. In the array implementation, we will print out how many pointer accesses were made when we use the data organized in a doubly linked list. So now let's look at the program. So the comparison program is this C file, right? It's called bin schcomp.c, standing for binary search comparison.c. That is the C program. And let us look at the interface files. I'm using a doubly linked list implementation, right? So let us look at the interface files, which would be interface.h, and let us look at the methods. So we have the same set of methods to compute the size, right? To check if a list is empty, and so on and so forth. These were the appropriate methods from the last lecture. But now there is one more method, right, which is called bin search. Right? It returns a pointer to doubly linked list node. It takes as argument two pointers, and it takes an integer query. Right? We'll talk about the meaning of the arguments in a short while. Right? So that is a new function that I have added. There is one more function, one more data item that I have added, which is the integer which keeps track of the number of pointer accesses. Right? It's called finding mid by binary search. Right? So this is an integer. Right? Now I'm declaring it to be an external integer. This will be used by programmers. Whoever uses the interface.h file will find this integer variable declaration here, right? And the definition of this variable and the way it is modified is present in the doubly linked list methods.c file. We are going to see that in a short while. So compared to the earlier implementation, this is the more current implementation. Additional methods have been added, and additional data items have been added. Right? In particular, I've added a method for the binary search, and I've also kept track of one variable, added a variable to keep track of the total number of pointer accesses that are made by binary search. So let us go to the doubly linked list methods.c file. Okay, so let us see, I've now defined this counter variable finding mid bin search, initialize it to 0, and as a remark below says, this counter keeps track of the number of times binary search has to find mid. For each mid query, the count is the total number of pointer traversals to find mid. I hope this is clear. That is, if you want to find the mid, you have to do a certain number of pointer traversals. For each mid query, we count the total number of pointer traversals and sum it up over all mid queries. That is the total amount of work that is done by binary search to find the mid element. We've also modified the dsize function, right? That is a size function which returns the size of the list, right? So this function is where this function is used to compute the size of the list of the doubly linked list between the nodes pointed to by head and tail. Right? So let us just look at this code very quickly. Okay? So let us just look at the recursive function call. The recursive function call, okay, shrinks the list from left and right. That is, the pointer moves to head pointer.next and tail pointer.previous. Right? Here are the boundary conditions. Right? If head is equal to tail, then you increment the value of count and return that value. Observe something very important here. Right? Here I reset count to 0 and return the value, return value. This is because count is a static integer variable. It must be returned set to 0. It must be reset to 0 for future function calls to work correctly. This is very important. So please pay attention. If count was not reset to 0, subsequent function calls to dsize may not give you the correct answer. So as a good programming practice, when you use static int with recursion, you must be very careful about the counter variable, right, which is a static variable. So when you use a static variable inside a recursive function call, you must be clear about what the role of that variable is. Right? Here, because I am repeatedly going to make function calls to dsize to identify the size of the list, after one computation of the size of the list, I reset count to 0 and return the value of a different container or a different variable. If head pointer.next is equal to tail, then we are essentially counting two new elements, two new locations. Therefore, count gets increased by 2. It gets reset and then I return the value. Otherwise, what does otherwise mean? That head is not equal to tail, head pointer.next is not equal to tail. Right? Which means head and tail are at least, between the two of them there is at least one more node. We increase the value of count by 2 and then make a recursive function call by moving the head pointer forward and the tail pointer backwards. That is, head now points to head pointer.next and tail points to tail pointer.previous. Observe that here in this implementation we are very carefully using features of the doubly linked list. Rest of the piece of the code are doubly linked list methods which are unchanged. Let us go directly to the binary search implementation. Okay. Okay. So let us just look at it. Binary search is the name of the function. It returns a pointer to a node in the doubly linked list. It takes a pointer to a node called start and takes a pointer to another node called end, and it takes in the query value. Mid is going to be the return value of the point which is going to contain the key if it is there. Otherwise, we'll return null. So let us look at some boundary conditions. Right? If start becomes null or end becomes null, right, we return null. Okay. This condition is a comes after function, which is a method internal to this module. I repeat, comes after is a method that is internal to the module, by which I mean that it is not present in the interface files. Right? So comes after of start and end. The role of the function is very clear. We check if end comes after start. So if end comes before start, then we return null saying that the key is not found. Right? So comes after is a very simple function. It's just a 2-line piece of code. Right? Let's just take a look at the comes after function. Well, it's just 3 lines. Comes after takes 2 pointers in a list. Right? If start is equal to end, it says 1. If start is equal to null, it returns 0. Otherwise, it moves the start's pointer forward, right, and it goes and tries to meet end. So it's a recursive function again. So as you can see, how recursion plays a very important role in writing programs to maintain data structures. Right? So we have so many recursive functions we've seen so far. So here is a comes after, which is a recursive function which checks if the end pointer comes after the start pointer. Right? Alright, so now let's go back. So comes after basically returns 1 if end comes after start. This one says that if end does not come after start, then you return a null. Now, if you've not returned, if the control has not returned from this function call and it comes here, it means that start and end, that is end comes after start and neither start and end are null. So now what you do is you compute the midpoint using the midpoint function. What does midpoint do? The midpoint function essentially returns a pointer to a location which is the median element in the list, where the first element is the start and the last element is end. Right? So let us just look at this. Midpoint is the function. We'll come to the midpoint in 1 minute. Let's complete the binary search. Right? So mid is essentially a pointer to the middle point of the list. Okay, for some reason if mid is equal to null, then you return null. Observe that this is an example of what I would call, or what is known as, defensive programming. Right? It's not a very meaningful condition, but I'm putting this as a safety check, saying that I will return null because in the next statement I'm checking if query is midpointer.value. Now this is very important because if indeed mid turned out to be null for some reason, right? Of course the logic, if you make meaningful function calls, then mid will never be equal to null. But then if meaningless function calls have been made along the way, and we don't know in how many ways meaningless function calls can be made, this is a safety check to ensure that the program actually exits meaningfully or returns some meaningful pointers. Right? And in this case, it returns a null pointer. And again, I assert that the reason that this comparison is there is because in the next statement, I'm going to check midpointer.value, right? And control will come to this particular statement, right? Only if mid is not equal to null. You can very well imagine that if mid was null and I did not make this check, then midpointer.value would be a meaningless pointer access which can cause the program to actually crash. Therefore, as a programmer, you must program in such a way that your program does not crash. You may not be able to handle all errors. Actually, no, you will not be able to handle all kinds of errors. However, you must design your program so that you can exit gracefully. A crashing program is not a good program. And therefore, this check is a kind of a defensive programming to ensure that the program doesn't crash here. Okay, so now here I check if query is equal to the value inside the mid pointer in that particular location. If it is, then you found the queried value, return the pointer. Otherwise, we set up the recursion. If query is more than the mid value, then we make a recursive binary search, recursive call to binary search, starting with the successor of mid right up to the end and the same query value. Otherwise, it means that query is strictly smaller than midpointer.value. Then you cause a recursive binary search from start to midpointer.previous and the queried value. So observe that we are using the properties of the doubly linked list here very carefully. All these are very simple single pointer queries. If this was not a doubly linked list, then computing the previous, as you know, was a very time consuming task. Multiple pointer traversals had to be made. So this is the complete implementation of binary search, assuming that the data is arranged in a doubly linked list. Right? Let's look at the midpoint function. So if you look at the midpoint function, again it takes two pointers to two locations in doubly linked list and it returns the midpoint. But along the way, I also do a little bit more of work here. I also compute how many pointer traversals were made to compute the midpoint. See this finding mid bin search. Remember, this is the counter variable to keep track of how many pointer traversals are made totally. Right? This is a variable global to this module. Okay? And center tells you that the number of pointer traversals that you will have to make is the size of the list divided by 2. That gets added to the previous value for finding mid bin search, and that's it. Everything is fairly straightforward. Here you loop right up to the center of the list and keep skipping to the next location till you come to the midpoint. Again, here is a bit of defensive programming. If mid becomes null for some reason, you just exit from the loop and return mid is null. Right? Again, this is a bit of defensive programming. Okay, so that completes the whole discussion about the implementation of the few additional methods. Let me just draw your attention to how many additional methods I have implemented. So the bin search is a method, midpoint is a method, and comes after is a method. So I have implemented 3 more methods in the doubly linked list data type methods file, right? But observe that only the last function is in the interface file. Therefore, if you are using this data type, right, you are not supposed to use function calls to the midpoint method and the comes after method. These methods are considered to be methods private to this module. Right? I will not say more about it. I have just introduced a very important keyword. Right? You are not supposed to make function calls to these methods which are not being put in the interface file. Okay? Of course, because they are not put in the interface files, if you try to use them, the compilation will fail. Right? It will give you a lot of error messages. Okay. So we are done with this part of the implementation. Okay. So we have augmented or added additional features to the doubly linked list methods file. We've added a binary search implementation assuming that data is in a doubly linked list. Now let us go to our comparison program. By the way, I have also compiled this, but I can compile this for you. gcc-c dll st methods.c. Okay, that compiled and a .o file has been generated. Okay, so the .o file has been generated. So now let's go to our binary search comparison program. This should not take too long, right? I only have one additional function prototype here, which is called a bin search in a doubly linked list node array. I repeat again, int, and int. The last int is a queried value, and the first 2 ints are indices in this particular array, right? And A stands for array. So therefore I have a binary search implementation assuming that the data is organized in an array and it returns a integer value which will be an index. I also keep a global variable counter called midprobes, which is going to count the total number of probes made into the array, okay, by the array binary search function. Everything is fairly straightforward. Let us just see this part. Here I'm going to read the array. Sorry, I'm going to read the number sequence into an array. Okay. And the function is called numRead. It's very interesting. Right? So what it does is it takes a pointer to the number doubly linked list. That's a first argument. The second argument is it takes an integer pointer to the array size. That is, the first element is just a single number has been read. Right? Just a single number has been read. Array size is now 1. It takes a pointer to array size and it returns a number array, and this number array is an array of doubly linked list nodes that contain exactly the same number sequence. Right? I repeat this. The numRead function is a very interesting function. It takes as argument a pointer to a doubly linked list called number. It also takes a pointer to an integer. This fellow will contain the total number of values which have been read from the input. That is what array size will consist of. It also returns a pointer to an array. What is the type of the array? The type of the array is a doubly linked list nodes. Right? How many elements are there in this array? The number of doubly linked list nodes which are there in this array is exactly array size. What values are there? Exactly the same values. Right? Why am I doing this? My goal, remember, is to compare binary search when the data is stored in a doubly linked list and when the data is stored in an array. Okay? So I'm kind of taking a shortcut, right, to make my programming easy, and I'm storing the numbers in the number array where the individual elements in each array are of type doubly linked DL node, and number is a doubly linked list itself completely. Okay? We'll go to that function in a short while. Then I then I read the search key from the input. Now I print the number list. Okay. Then what do? I call binary search, which is there in the doubly linked list methods.c. I give it the number. I pointer to the first element in the doubly linked list, and then I give a pointer to the last element in the doubly linked list called number. Then I give the search key. If it is not equal to null, then I print found. Right? Remember that the binary search function, right, returns a pointer to the location if the key is found, and if the key is not found, it returns a value null. Right? If it's not null, it prints found. Otherwise, it just prints the cost of the total number of pointer traversals by printing out the value of finding mid binary search. Then again it prints the contents of the number array. Okay? That is the same number sequence is present in this array. I perform an array bins binary search on number array starting from the index 0 up to array size, which is the total number of keys. Right? And search key is another argument, and this fellow returns the value into the variable called location. Right? Indeed, you will see that the implementation guarantees that if the key is not there, it returns a value -1. Otherwise, it returns a value in the range 0 to array size -1. It says it is found at a particular location, and it prints the total number of mid probes, which is the focus. Therefore, what have we done? We've completed the implementation of binary search, one on an array, the other on a doubly linked list, and we have printed out the statistics of the number of probes for finding the middle element, and here the number of probes for the middle element, which is a single arithmetic operation. Alright, so let us just quickly look at the read function. Okay, so let us just look at it. This is a pointer called values count. It's a pointer to the list of numbers. This is a doubly linked list of numbers, and the return value is a pointer to a doubly linked list array, right, which I call a return array. So let us just see this. You read an integer from the input buffer. So if the read was successful, the read value will contain this, that is, it will have a positive value. Remember that what scanf does, the return value of the scanf is the number of data items that it successfully read. That is, if you said read an integer, one integer, then scanf will take the value 1 if the read was successful. If the read failed, that is, if you put a non-numeric character there, then scanf will fail and this fellow will take the value 0. So therefore, as long as scanf succeeded to read one integer, that is what the meaning of this expression is. Go ahead and do these steps. What are these steps? Okay, you create a node of, you increase the size of the doubly linked list. You create a node, you put the value inside the value field, then you make the next pointer go to null, then you make the previous pointer point to the last element of the current number list, then make the current number list point to make the newly added node the last element. That is what you repeatedly do here. Okay, now here comes a bit of C programming which should be interesting for all of you. When control exits from this while loop, it means that this scanf failed. Scanf also, what it does is, if it fails, it returns the data, the last value, it sends it back into the input stream. Now the input stream must be flushed, because after this we are going to read the search key. The way it is done is using this function call which is there in stdio called fpurge. Right? If you're programming on a Unix system, then you should be able to get access to the fpurge function call, please read it, right? And you will understand what it does. So it is because scanf sends the value back into the stream, and we don't want that value in the stream. We want to throw it out. So we purge the std. Now what do? Another node now points to number. Right? Therefore, number and another node now point to the number list that we have read so far. Okay, now what do? We know the total number of elements which are there in the input list. We create an array of that size. Right? Let us see this. This is the statement. Right? The result is an array. That is, this is a pointer. calloc is contiguous alloc. It has two arguments. How many locations and what is the size of each location? The first argument is how many locations, and the second argument is size of each location. Therefore, the result of calloc is that we have created an array of DL node data type. Okay? And you may be worrying why I am doing this. It also shows you how to use calloc. That is one purpose, but it is also the comfort of implementation. Okay? Okay, so now let us see how to make a copy of the number list which we have read into this array. That is what this loop does. I've initially initialized index variable to 0. I do this till index is less than or equal to the total number of values that we have read in. Right? All that I do is value is set to the another node dot value. So essentially we iterate over the list and make a copy here. Right? So let me just put a remark here right in front of you so that you appreciate it. Make a copy of another node in. This is what we have done. Okay. Now you return array. Now let us look. The result of execution of this function is very interesting. There are three side effects, three effects that have happened. You read the number into this doubly linked list. You have also communicated the total number of values that you have read by this particular pointer. Then you also returned a pointer to an array. There are three effects of this array, and this is what is very interesting. Right? The kind of things that you can do. Right? Though people may believe that you can only return a single value from a pointer, from a function. Using pointers, you can actually do fairly sophisticated, dangerous things if you're not a careful programmer. So this is the numRead function. Right? As you can see, it not only reads the whole list into an array, the whole list into a doubly linked list, but it also creates a copy of it in an array. It also returns a value of the number of keys that have been written. Print list is not any different from earlier. It just prints the contents of the doubly linked list. In this case, it can also print out the contents of the array. Right? That is the reason I have chosen the array of the same data type. I don't have to write another print function. Okay, now let's look at the binary search implementation. It is very straightforward. It's the same thing. Right? Number array is passed to the function. Two specific indices start and end are passed to the function, and the query key. Okay. Now I have an integer variable called mid. Okay. So if start is more than end, I return -1, saying that the key is not there. This is indeed the correct exit condition for binary search in an array. Otherwise, start is less than or equal to end. I have to make one more probe to the mid of the list. So I increment the mid probe by 1. Then I compute mid, which is start plus end by 2. Now I check if the queried value is in the mid location pointed to by mid. If it is there, I return that particular integer value. Otherwise, the two recursive subproblems are generated exactly as we did in the doubly linked list case, except that observe that mid is created by a single arithmetic operation. A single arithmetic operation to compute mid, as opposed to what it was Recall that in the doubly linked list, it was many pointer traversals. Here it is just a single arithmetic operation. That is the only difference between the two implementations. So that completes the whole program. Right? Let us see what we have done in this program. We looked at the doubly linked list data type. We have added an additional binary search function to it. We are going to compare it with the array implementation. Right? Therefore, we have a very interesting reading in function where we read in the same sequence of sorted sequence of numbers into a doubly linked list and into an array, and then we implemented binary search on the array also. So now we are in a position to compare it, and we've already observed that we print out the number of probes, right, in both the places. Fine. So therefore we are ready to compile and execute this program. So the compilation is gcc bin sch comp.c. I want the output to go to bin sch comp, and I want to list this particular object file which has been pre-compiled. Right. The compilation is succeeded. Now let's go to running this program. .bin sch. Right. Okay, so it's waiting for an input. Let us see what the input is. Let's give it in sorted order. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. Let me make it 11, 12, 13, 14, 15, 16. Just a power of 2 so that you can see the effect of log. Now, the reading will fail when I give it a non-integer. Let me give it A. Now A has been read, the input array has been read. Now it's waiting for the search key. Let's give the search key to be 2. It's an easy check. Right? Observe that the response is that it has been found. Right? The cost of pointer traversals, it has made 15 pointer traversals. I'll encourage you to do this by pen and paper to calculate that 15 pointer traversals are made. Then the contents of num array have been printed out. It says that it has been found at index 1, but the number of mid probes is 3. Right? Let's see. The midpoint of a 16 sized array is 8. Then the midpoint of an 8 sized array is 4, 2 mid probes, and midpoint of a 4 sized array is 2, and the last probe will find the given key. Right? This is for a successful search. Let's do it for a failing search. So it's important also for you to notice that the input has to be correctly given. I am not checking that the input is in sorted format. If the input is not in sorted format, this algorithm is not guaranteed to work. Let's give the value 17, which is not present. So as you can see that if you use an array with 5 probes, the array implementation discovers that the value is not in the list, whereas the total number of pointer traversals is almost the total number of elements in the list. That is, it is 12. It is of the same order of the size of the list, whereas here it seems to be of the order of log of the size of the list. Let's do this for a larger array just to make this comparison. Let's do this for 32 elements. So you will see that, okay, let's do a failing search. Let's search for the value 33. Okay, now I have to print a non-number, which is A. Now I have to print the value that I'm searching for, 33. Okay. As you can see, it's made 27 pointer traversals, but the number of mid probes is only 6. That is one more than the case it was for 16. Now for 64, you can check that it will only perform 7. Right? And this should be almost of the order of 50. Okay. So maybe just for your benefit, let me just type the whole thing down. Okay, 64 keys in input. The whole list has been given. Let's search for 65. As you can see, the total number of probes is nearly the whole doubly linked list has been probed. Right? That's 58 probes. Whereas observe that the array implementation has just made 7 probes into the array to discover that the element is not found. Right? So this completes the whole discussion of the comparison of the binary search implementation on a doubly linked list with the binary search implementation on an array. So it's quite clear that the binary search implementation on an array is very efficient in terms of the total number of probes. So therefore, what have we done during this week? We have studied 3 data types, right? Linked list, doubly linked list, and arrays. We have taken 2 algorithms. One algorithm was the big number arithmetic. We did only big number addition. But you'll recall that the polynomial multiplication exercise that I've given is also a very simple, more general big number arithmetic. Linked list and doubly linked lists are compared. We notice that doubly linked lists are faster but use more space. Then we compare doubly linked lists and arrays for binary search on a list of sorted data. With arrays, we perform lesser number of basic CPU operations. That is, we find the middle index based on one arithmetic operation, whereas in a doubly linked list, we find the middle index by multiple pointer queries. Therefore, one can imagine that arrays have the power of hardware support and the compiler support of random access. And the access based on a given base value and an offset. This is not very important, but if you understand a bit of computer organization, if you've already studied it, you will immediately appreciate it. So therefore, when we meet in the next set of lectures, we are going to look at the abstract data type stack and queue, and we will see how recursive algorithms can be implemented without the use of recursion, but with the use of a stack. Right? So that is going to be the focus for the next week. And this brings to an end today's lecture. Thank you very much.